So if everyone is ready, then we'll continue with Jiaming Su from Duke, who'll tell us about planted matchings, perhaps.
Okay, yeah, thanks for the introduction. And thanks for coming to my talk. Today, I would like to talk about one of my recent work on testing network correlation. So this is a joint work with Yihong Wu at Yale and then Sophie Yu at Duke. I think they are all online, so they might help me to answer the questions that you have during my talk. So let me get started by first recalling the graph isomorphism problem. So given two graphs A and B, graph isomorphism is to decide whether A is isomorphic to B, or in other words, whether there exists a bijection pi between the two vertex sets such that every edge in A is mapped to every edge in B. So here is a classical example illustrating the difficulty of graph isomorphism. So in these plots, even though the two graphs appear to be rather different, but they are in fact are isomorphic to each other. So the underlying isomorphism is given as follows and also highlighted using the same colors in the plots. In the worst case, the graph isomorphism is actually not known to be solvable in polynomial time. And you can imagine in practice, we can encounter a more difficult scenario that two graphs may not be exactly isomorphic, but we're still interested in telling whether their topologies are similar. So fortunately, real networks are arguably not necessarily in the worst case. So this consideration motivates us to move beyond worst case and consider graph isomorphism in the average case. So in particular, we consider this noisy graph isomorphism problem as a hypothesis testing problem. So suppose we observe two random graphs A and B. Under the non-hypothesis H0, A and B are independently generated. And under H1, suppose there's a latent node correspondence given by this uniform permutation pi. And then under this latent node correspondence, A and the permuted version of B pi actually are edge correlated in the sense that Aij and B pi pi j are correlated random variables. Now, the goal is to distinguish these two hypotheses based on observation of this single realization of these two random graphs A and B. So note that under this alternate hypothesis, this inherent edge correlation is actually obscured by this latent node correspondence pi, which makes this problem challenging. And also as a result, the test that you develop needs to rely on so-called graph invariance, the graph properties that are invariant on the graph isomorphism. For example, like the subgraph count, like the number of triangles or edges, or like the spectrum, like the eigenvalues of adjacency matrices or Laplacians. In our work, we actually consider two special settings of this general setup. One is the Gaussian setting, the other is this Erdős-Rényi setting. So for the sake of time in this talk, we're going to focus exclusively on this Erdős-Rényi setting. So this setting was first proposed and studied by the previous work by Reich et al. In particular, under non-hypothesis, the two graphs A and B are just independent Erdős-Rényi random graphs with n vertices and then edge probability P times S. Under alternate hypothesis, again, there's underlying latent permutation pi. And under this latent permutation, A and the B pi actually are independently edge subsampled from a common parent graph that is Erdős-Rényi, Gn comma P with subsampling probability S. So in other words, here we assume that there's a common parent graph that is Erdős-Rényi, and then every edge in this parent graph will be included in A with independently with probability S. And then we kind of repeat this edge sampling process to obtain the second graph B pi. And as you can see, since both graphs are subsampled from this common parent graph, so they are correlated in edges. But note that if you check under both H0 and H1, marginally, both two graphs actually are Erdős-Rényi with n vertices edge probability PS. But under H1, then with the correct node correspondence, the pair Aij and B pi pi j are correlated Bernoulli random variable with correlation actually given by this formula here. So roughly speaking, when P is small, the correlation is roughly given by this edge subsampling probability S. Okay, so if S is higher, that means this correlation is higher. So these two distributions will become more distinct. I should also mention that the problem here is actually a hypothesis testing aspect of this graph matching problem, where for the graph matching problem, the goal is actually to recover this underlying permutation under the alternate hypothesis. So this talk, we consider this hypothesis testing version, and we want to understand when we can distinguish these two hypotheses. So let me now first present our main result. So first, we derive a sharp threshold for detection in the dense regime. So recall that n is the number of nodes, p is the edge probability, and s is the edge subsampling probability s. Okay. So we show that if s squared is bigger than this expression here, then the total variation distance actually converging to 1 as n goes to infinity. Conversely, in the dense regime, when the edge probability p scales as n to the power of minus little of 1, then we almost get a matching like negative result. So when s squared is less or equal than 2 minus epsilon times log n divided by this expression, where epsilon is any arbitrarily small constant, positive constant, then the total variation distance actually converging to 0. So pictorially, you can visualize the results using this following phase diagram. So here, the x-axis is the kind of, you can view as a rescaled correlation that is given by this nps squared times log 1 over p minus 1 plus p divided by log n. So under this rescaling, then basically, if you look at the asymptotic value of total variation distance, this actually jumps from 0 to 1 at a sharp threshold 2. Okay. So below the threshold, even the weak detection is impossible in the sense that it is impossible even to strictly outperform just randomly guessing the hypothesis. And then above the threshold, we can show that strong detection is possible in the sense that you can correctly distinguish these two hypotheses with a vanishing error probability.
So Jiaming, just to check, this is corresponding to the case where the sort of intersection graph has average degree log n?
It's actually more than average degree log n. So the average degree under the intersection graph is actually nps squared. So if you view that is nps squared bigger or equal than log n divided by log 1 over p. So this is actually a regime where the average degree intersection graph actually converging to infinity.
Okay.
Sorry, can you say what you mean by the intersection graph here?
Oh, right, yes. So the intersection graph, basically you have two graphs, and then the intersection graph just means the graph actually includes all the common edges in the two graphs. So you have aij and you have bij. So the intersection of A intersection B is just all the edges included in both A and B. So since you want the edge to be subsampled twice, so that's why you have s squared. So that's why the edge probability is like p times s squared. So the average degree is n times ps squared. So the condition here requires that like you need nps squared to go to infinity to be able to achieve a strong, like the total range distance actually goes to 1. Okay.
So sorry, so does this
yes.
mean that if I did exhaustive search over all permutations of the vertices so that I would found a B which has a large intersection with A?
Yes,
so
okay. I'm actually going to talk about later like how we get this possible result, and that's exactly as you suggest. We're looking over all the possible permutation and then compute the maximum correlation between the two graphs. Okay, so we also obtain similar results for the sparse regimes, but the picture here is slightly less clear. So we still have the positive results that I stated earlier, but for the negative results in the sparse regime, we're focused on P like scales as n to the power of minus constant, then we're able to show that if s squared is less than roughly minimum of 1 over np and then 0.01, then the total variation distance is actually bounded away from 1. And furthermore, if s squared is less than the minimum of 1 over np and then a little of 1, then the total variation distance is actually converging to 0. Okay, so roughly speaking, the negative results here combined with positive result allow us to identify the threshold within a constant. So let me mention a special case to illustrate the result. So if you look at the constant average degree case where P is equal to some constant D over N, then these results imply that the strong detection is possible if S squared is bigger than this constant 2 over D, but it's impossible if S squared is less than 1 over D and the minimum of 0.01. Okay. Okay, so after identifying the statistical detection limits, a next level question is, can we achieve this limit efficiently? And so a simple kind of testing statistic to consider is actually just based on counting the edges in the two graphs. And then if the number of edges in two graphs is very small, then you declare that is in the alternate hypothesis. And this turns out to achieve weak detection in linear time when the S is above a constant. Now, the previous work by Barak et al. Actually consider more sophisticated subgraph counting. So in particular, they consider counting so-called balanced subgraphs of constant size, and they're able to correctly distinguish the two hypotheses with the correct probability at least 0.9 in polynomial time, if again, S is above a constant, and then the average degree fall into this particular range. So this condition here is because of their special construction of the balanced subgraphs. More recently, like in a companion work, we actually obtained some new results in the sparse regime based on counting certain weighted trees of growing sizes. And this is actually inspired by the low degree polynomial approximation of likelihood ratio. So in particular, we're able to show that by counting the weighted trees, we can achieve strong detection in polynomial time when, again, S squared is bigger than this constant, and then also when the average degree is actually in this range. So this constant actually comes from the number of unlabeled trees of a given sizes. So this result is an odd optimal in the sparse regime when you have an average degree. So the positive result here comparing to the negative result differs by a constant factor. So even despite these latest developments, I think a big open question in this problem is that whether there exists polynomial time test for sublinear S. And this question is still widely open. In the remaining time, I would like to actually talk about how we prove these results briefly, and also try to highlight some of the new kind of proof ideas. So the proof of possible result is actually relatively simple. So we consider this particular test statistic, that is computing the maximum edge correlation by maximizing all the possible latent node correspondence. And this optimization problem is known as quadratic assignment problem, and is NP-hard in the worst case. So that's why this test statistic is not computationally efficient in the worst case. As desired, this statistic is invariant to the node relabeling. Okay, so if you relabel the nodes in A and B, the test statistic, the value won't change. And the proof of the success of this statistic is relatively simple. It's just based on the same first moment calculation, or like using a union bound. But I want to mention that the proof of negative results is much more interesting and then also much more challenging. So I would like to focus on in this talk. So in particular, we apply this so-called second moment method. So it is well known that if we can show the second moment of the likelihood ratio is bigger of 1, then the total variation distance is actually bounded away from 1. Okay, in this case, the strong detection is impossible. If you can show the second moment of likelihood ratio is 1 plus little of 1, then this implies the total variation distance actually converging to 0. So even the weak detection is impossible. So with this result, now our task just reduced to computing this quantity, the second moment of likelihood ratio. So to do that, I need to introduce the cycle decomposition permutation. So just let me briefly review that. So given a node permutation sigma, it can always naturally induce an edge permutation, which I called sigma superscript E here, on the n choose 2 unordered pairs as follows. Okay, so in particular, sigma superscript E and then apply to ij just equal to the edge sigma I comma sigma j. Now, let me give you an example to illustrate the cycle decomposition. So let's consider a simple case when n is 6 and sigma is given by the following cycle decomposition, where we have one fixed point and then 1, 2 cycle and then 1, 3 cycle. So now, based on this, you can naturally write out the cycle decomposition for the induced edge permutation. So for example, the 2 cycle in the node permutation actually induces a fixed point in the edge permutation because you can check that 2, 3 map to itself under sigma. Right. You can also see that if you take 1, 2 cycle in the node permutation and 1, 3 cycle in the node permutation, this induces a 6th cycle in the edge permutation just by considering all the pairs 2, 4, and then the corresponding mapping will become 3, 5, and so on and so forth. So I want to mention that this cycle decomposition of edge permutation actually gives a partition of all these n choose 2 pairs. And in these talks, I'm going to call the cycles like orbits. So the cycles in the node permutation will be called node orbit, and cycles in the edge permutation will be called edge orbit. So now with this cycle decomposition, then we can proceed with the second moment calculation. So the important thing here is that under the alternate hypothesis, the distribution P is a mixture distribution, mixing over this underlying latent permutation. So you plug in this mixture distribution, you take square, and this will naturally induces 2 independent copies of permutation pi tilde and pi, with the product of xij, and each xij is nothing but the likelihood ratio of the corresponding pair. And now here with the cycle decomposition, then we can regroup the product according to the edge orbits, the orbits of the edge permutation, where here I would mention sigma is actually just the difference between pi and pi tilde. And now with that, then we can take expectation over Q over both hand sides and then interchange the expectation. So now the important thing is that why we need the cycle decomposition is because the edge orbits are disjoint. So XO will become independent across different O. So that's why we can pour the expectation inside the product and we arrive at the expectation of XO, where XO, remember, is just the product of Xij over all the pairs in this edge orbit. It turns out that this expectation of XO can be explicitly computed, even though the computation is complicated, but we get this nice simple expression. So it equals 1 plus rho to the power of 2 times the length of the edge orbit, where rho is just the correlation coefficient. So this means that for the longer orbits, it actually contributes less to the second moment. And this we will actually utilize later in our proof. I also mentioned that how to get this expression, we use this so-called Igoryshev method to kind of use the control integral representation of the binomial coefficient. So that's how we get this formula here. And now with that, then we can combine everything, and then we can show that the second moment of the likelihood ratio is actually equal to 1 plus little 1 when rho square is smaller than 2 log n over n. But unfortunately, when rho square is bigger than 2 log n over n, this actually blows up to plus infinity. And then if you compare the negative condition that we get here with the condition that we present earlier, this condition is actually suboptimal by a bounded factor when p is small. So somehow we need to revamp the second moment to show a tighter result. So to do that, we need to understand like what causes the second moment blows up, even though the total variation distance remains small. Okay, so it turns out that the second moment blows up due to this obstruction from these short orbits. So one easy way to visualize this or to see this is to consider the lower bound by considering the scenario that these 2 independent permutation pi tilde and pi coincide with each other. And this happens with a very small probability, 1 over n factorial. But when this happens, then the edge permutation just reduced to n choose 2 fixed points. So that's why you have this 1 plus rho squared to the power of n choose 2. And then if you check that, this expression actually blows up to infinity when rho square is bigger than 2 log n over n. And that's precisely the reason why the second moment blows up. So this calculation, you can actually carry out a similar calculation even for short orbits beyond fixed point. And you will see that the second moment still blows up, but at a slightly different threshold because of short orbits. So the crucial observation that we get from here is that the second moment blows up because of this atypically large magnitude given by this product of XO for short orbits of length k up to log n. So if we want to make sure the second moment is bounded, somehow we need to regulate the product XO for those short orbits. And this actually give rise our like this so-called conditional second moment. So in the dense regime, this is relatively simple to do because it suffices to consider fixed point. In particular, it suffices to consider the edge orbits of length 1 and this product XO for all these fixed point roughly equals 1 over p raised to the power of 2 times this quantity here. So f here is just a set of fixed point of this node permutation sigma. And this A intersection B pi is just the intersection graph that we mentioned earlier. So this is the graph that includes all the common edges in A and B pi. And now this E, this quantity here is nothing but the number of edges of the subgraph of this intersection graph induced by the fixed point in the node permutation. So if this subgraph induced by F is dense, then this will create a large magnitude of product XO. So we need to somehow regulate the subgraph density. And here I want to mention that the F depends on pi and pi tilde. So it's impossible to directly regulate or control the subgraph density over the graph induced by F. So that's why we actually instead consider a uniform concentration. So luckily, under the alternative hypothesis P, then actually for every subgraph S, the subgraph density, the number of edges actually concentrates uniformly, as long as the subgraph size is large. So now we can conditional on this typical event under this P, and then when the cardinality of the fixed point is large, then by putting an indicator here, this naturally induces a control over the maximum possible value of the number of edges induced by F. And then you can compute this calculation, and that's how we prove the result in the dense regime. For the sparse regime, it turns out that the situation is much more complicated. That is because we need to consider all the edge orbits up to length log n. So we divide our analysis into 3 different categories. The first one is the long cycles, like those orbits of length above log n. And turns out that for those long orbits, they contribute 1 plus little 1 to the second moment already by just plugging the vanilla second moment calculation. Now we're left with a short orbit. So we'll further divide into the case where the orbit as a set of edges is not totally included in the edge set of the intersection graph. In this case, it turns out that we can directly bound the expected value of XO. So it's already upper bounded by 1. So the only trouble comes from these short complete orbits, those orbits that are completely included in the edge set of the intersection graph. Because at this case, the XO actually induces the maximum possible value, that is 1 over p to the power of 2 times the length of O. So somehow we need to control like the number of such short complete orbits. So that's why here we actually impose a condition nps squared less than 1, because in this case, since the intersection graph, the average degree is actually bounded away from 1, so this is actually a pseudoforest. It's in the subcritical regime. So it's a pseudoforest with high probability. So the pseudoforest here just means that every component in this graph having at most 1 cycle. Okay, so because of this pseudoforest constraint, this naturally limits like the number of complete orbits that can occur in the intersection graph. So in particular, we look at this union of all the edge orbits, short complete edge orbits. We call it HK here. And HK is again a subgraph of intersection graph. So it is a pseudoforest. So we're going to use this pseudoforest constraint to control the expected value of product of XO for short complete orbits. So that's what we are going to do. So conditional on this high probability event that the intersection graph is a pseudoforest under P, then we're able to bound the expected value of product XO for those short orbits. And this turns out to be, can be upper bounded by just the generating function of the pseudoforest that can be generated from the edge orbits of length at most k. Okay, so in particular, now the next step is to bound this generating function. So the key challenge left is to enumerate this orbit pseudoforest, somehow using the orbit structure. So here it is crucial to use the orbit structure, because if you don't use the orbit structure and just treat this as a general pseudoforest, the resulting bound of the generating function won't be enough. So the next thing for our enumeration is try to understand the edge orbit structure. So in particular, we classify the edge orbits based on how they are generated into the following 4 types. The first type we call the matching, like denoted by M. This actually is generated by the 2 node orbits of same size. For example, here we have 1 node orbit 1, 2, and 1 node orbit 3, 4. And this will generate an edge orbit 1, 3, and 2, 4. If we view this as a graph, this is just a matching between the nodes of the node orbit of the same size. So that's why we call it a matching type. The second type is called bridging. This is actually generated from the node orbits of different sizes or lengths. So for example, here we have 1 node orbit of size 2 and 1 node orbit of size 4. And then the edge orbit generated can be viewed as a bipartite graph between the nodes in these 2 node orbits. And that's why we call it the bridging. The last 2 types actually are just the edge orbits generated within the same node orbit. So for example, the type C edge orbit is just a cycle within this node orbit. And then type S edge orbit is just splitting this node orbit into 2 parts. So after identifying these different types of the edge orbits, we need to understand how these edge orbits can co-occur in the graph under the pseudoforest constraint. So the first thing is that the type C edge orbit is already a cycle, as you can see here. So under the pseudoforest constraint, you cannot have multiple type C edge orbits within the same component. Also, a very important property for the bridge is that if you look at this type B, M, L edge orbit, where L is the length of the shorter node orbit, and M is the length of the longer node orbit. So as you can see here, L divides by M. So the bridge is actually cycle free. But otherwise, if L does not divide M, you will discover that it contains a component with at least 2 cycles. So under the pseudoforest constraint, you can only have this type BML edge orbit when L divides M. So the key to our enumeration is try to identify all these possible forbidden co-occurrence patterns for edge orbits under the pseudoforest constraint. So due to the time constraint, I won't go into the details about our enumeration, but I just want to briefly...
Sorry to interrupt, just going to mention that so that we have time for questions, your time is kind of close to over, so it's a good time to wrap up. Yeah.
Yes. So I'm not going into the details about enumeration, but I just want to mention that we crucially use the edge orbit structure to enumerate the possible edge orbit pseudoforest. So after getting so this is actually our final bound on the generating function. And after getting this, the last step is to take the average over the permutation. And this step, we actually use the Poisson approximation of the number of cycles in the node permutation. Okay, so let me conclude my talk. So in this talk, we formulated the problem of testing network correlation and characterized the statistical detection limit. The impossibility proof actually applies the conditional second moment method. The sparse setting is particularly challenging. We leverage this pseudoforest structure of the subcritical Erdős-Rényi graphs. And we also see that there exists a large computational gap between the statistical computation limits. So the open problem is to derive sharp detection threshold in the sparse regime. And another open problem is to prove the existence of or try to close the gap, the computational gaps. So for more details, you can check the archive print. And thanks.
All right, thank you very much, Jiaming. Yeah, we got some great applause. Great, so our next talk is in 9 minutes, so we have plenty of time for questions. So if there's anything that you'd like Jiaming to go over, or you have some questions for him, let's hear them.
I have a question.
Sorry, I have 2 questions.
Oh, I'll go after Jane.
Okay.
Oh, you can go first. Chris, you can go first. Oh, yeah, it's me.
Go ahead, Jane.
Oh, hi. Yeah, I just wonder if this strong detectability property has the following convex property. So if I'm giving you two probabilities, P1, P2, say they are asymptotically the same, and you have G and P1 and G and P2. Now I'm just giving you a random graph that's, you don't know its distribution, but it's strictly between NP1 and G and P2, right? So it's a subgraph of the larger one and contain the other one as a subgraph. So now you know the results for the 2 ends. Can you actually say something about the detectability for the one that's sandwiched by these 2 GMP?
I see. Yeah, so I think like one thing that you can say maybe is based on like the property of the total variation distance. So if you, because all this detectability boils down to computing the total variation distance, right? So if you can derive the total variation distance, and for the setup that you described, then I think you can get immediately the the condition for the detection. So in other words, if you look at the graph sandwiched between these 2 endpoints, so if you can derive the total variation distance, then I think you can get the result that you want. But I don't know exactly whether this is possible to derive the total variation distance bound on top of my head right now. But I think that's something that something can check. And also I want to mention that there's a data processing inequality. So if you can construct some Markov kernel, then this also naturally induces total variation bound.
Okay, so the second question is, have you ever considered the parent graph to be sampled from other space, like random regular graph, for instance?
Yeah, so actually in this work, so we haven't thought about that, but indeed you can consider other possible graph family for the parent graph. Like one thing that I don't mention in this talk is that the Gaussian setting. So the parent graph is a complete weighted graph with a Gaussian weights. And then you can think about, you have 2 graphs that are corrupted version of this parent Gaussian weighted graph. So that's one possibility. And then for the regular graph, actually, I haven't thought too much along that line, but I think that can be also considered under this framework.
Thank you very much.
Yeah, you're welcome.
Okay, Chris, you want to go ahead, and after that, I'll have a question from the audience.
Sure, Jiaming, I just want to make sure I understand kind of the analytic heart of your calculations. So yeah. If I understood correctly, the likelihood ratio that you get is a generating function of the cycle structure, where a cycle of a given length has, contributes something which exponentially decays in its length, and then maybe there's also something for the number of cycles. Is that correct?
Yes, I think that's more or less correct. So basically, yeah, so you're right. So if you look at the square of the likelihood ratio, this just boils down to the expectation of the product of the bunch of contributions from orbits of different lengths.
Good. And so, yeah, the reason I ask, so as I'm sure you know, like this generating function for uniformly random permutations is a kind of classic calculation. So what you've done here is calculate the analogous generating function for the permutation induced on the edges by a uniformly random permutation of the vertices. Is that correct?
Okay. I think it's related, but I don't think it is exactly that. So for example, the generating function actually indeed comes from, in the sparse case, basically is that in this case, the contribution from this so-called short complete orbit just reduced to this 1/p to the power of 2 times the length of O. So basically, to control this, we just need to understand how many such short complete orbits can occur in this intersection graph. So, I mean, it's related to the random permutation, but it's not directly just a property of random permutation. So it also relates to this intersection graph that I want.
Okay, well, we can take this offline. I was just wondering if there was some beautiful sort of representation theoretic way to do this calculation, since we can, you know, the permutation induced on edges, you know, there are ways to understand that representation of permutations.
Right, so maybe I want to distinguish two things. One is what I call edge permutation. So that is, the edge is in terms of complete graph. So that's why every node permutation just naturally induces an edge permutation, including all the pairs. And then the second thing here is edge can also occur in the intersection graph. So that is a random graph. So there, the edge is really about this random graph structure, the Erdős-Rényi random graph structure. So I think what I want to say is that this generating function is not just about the property of this permutation itself, but also involves the random graph.
Okay, great. Well, and of course I was—
sorry, yeah, okay, maybe I should take it back. So like after done the computation, in the end, the generating function just boils down to—
after you take the expectation over the graphs. Good, good, okay. Because then I was going to ask you about the hypergraph version where we would have the induced permutation on triples or larger tuples of vertices from a uniformly random permutation of the vertices, and that seems like a nice direction to go.
Jiaming, I have two questions from the audience, which I hope we have time for. One is from Anirudh Sridhar, maybe more of an algorithmic question. The question is, can your results on hypothesis testing be extended to recover anything about the true vertex correspondence, the permutation, in the case that they are correlated?
Not directly, because here, as I said, we focus on this hypothesis testing version of the graph matching. So the results here do not directly kind of imply, for example, some algorithm or some result about graph matching, like recovering the latent permutation. So yeah, it's just a difference between the hypothesis testing and then the recovery or estimation.
Just a quick comment on this. Sorry, but what about the impossibility result? Is there any case you can get from the impossibility of detection, impossibility of recovery?
I see. Yeah, that's a good point. So I think right now we don't know the rigorous answer for that, but I think it is possible, for example, from the impossibility of detection to get some impossibility of recovery. But at this moment, I'm not sure. So that's often just, to my understanding, is often case by case. So for this particular problem, I haven't done the calculation.
Jiaming, we have a question also from Shuiyan Niu, who asks, could you elaborate on how the total variation distance is related to the hypothesis testing problem? The total variation is symmetric with respect to the two graphs. Are the two hypotheses H0 and H1 also symmetric?
Okay, so I don't fully catch the question, but in terms of total variation distance and then also the detectability, so I think the sum of type 1 and type 2 error in the hypothesis testing problem is just 1 minus the total variation distance. So if you can show the total variation distance, for example, is 1 plus lid of 1, this directly implies the sum of type 1 and type 2 error is vanishing. On the other hand, if you show the total variation distance is bounded away from 1, that just means that you need to suffer some constant error probability for sum of type 1, type 2 errors. So that's the connection that I know.
Okay, thanks. Maybe if Jess could set up slides. And Jiaming, actually, there is one more question from Salil. I don't know if you want to squeeze it in.
Okay.
Oh, we have two more questions. Oh boy. Well, maybe it's best we just continue with the talks, actually. Sorry about this, but like Bryce, we had a question from Bryce Wong, and we also had a question from Salil Schramm. So if the three of you could get together at some point and ask your questions, that'd be great.
Yeah, sure.
Okay.